We'll dive right in today with where we were when we ended last time. We've been talking about the aldol reaction and talking about how crossed aldol reactions are difficult. That is, when you have two carbonyl compounds, but you want one to be the enolate nucleophile and the other to be the carbonyl electrophile. And one strategy that I alluded to was, and this is perhaps the most versatile of the ones we talked about, is that you use a really strong base like LDA to make the enolate out of one carbonyl compound in 100% yield first, before you even introduce the other carbonyl compound. Then, in a second step, you introduce the electrophile. And if you're careful and you keep it cold, it tends to work out well. So here's an example of how to do that. We'll start with just our generic acetone ketone that we want to be our nucleophile. And noting that the pKa of a proton that's alpha to a carbonyl is around 20. And we're going to use LDA as the base, noting that LDA is really strong as a base because its conjugate acid has a pKa of 40. So you can hope to use in the first step LDA to completely 100% yield deprotonate the carbonyl compound to make your enolate. And you expect that in 100% yield because the conjugate acid of LDA is really, really not acidic. It has a pKa of 40. So the equilibrium for constant for this reaction is like 10 to the 20. It's really, really, really favorable. A couple of things about this reaction, just some things that you may see in your text. One of the things you do is you keep this reaction at low temperature. The reason for that I'll tell you in just a minute, but you'll sometimes see the annotation either right by LDA or below the arrow, minus 78 degrees Celsius. What they mean by that is you're keeping it cold. And now we have easy modern refrigeration techniques that can make a round bottom flask. You immerse it in a bath of some liquid, and then you have a refrigerator coil that keeps that liquid really cold. In the old days, or even still, if you don't want to use that, you can take some dry ice and immerse it in acetone and then stick your round bottom flask in that, and that'll keep it cold around minus 78. In fact, nobody actually in the old days actually measured the temperature. They just put dry ice and acetone and said that was minus 78. So that's what that means. The other thing that you will see in problems is they'll tell you what the solvent is. Of course, since you're using LDA, the requirement is you need a polar solvent, but one that is aprotic, meaning no acidic protons. So good examples, good options for solvents for this reaction are often ethers. Diethyl ether is one of these. That's abbreviated sometimes as ET2O. There's another one, a 5-membered ring ether called THF. And you don't need to put those down when you're proposing a synthesis, but I do want you to not be distracted by them when you see them in a problem. I know that sometimes when you encounter something that's unfamiliar, your first response is to freeze up and not know what to do and to not even be willing to take a chance. And I just need you, when you see a problem set, to mostly acknowledge that, yeah, we're at low temperature, so this reaction will work. We're using an ether solvent because we don't want any acidic protons, and then move on. Okay? Yeah?
What if we wanted the more substituted enolate? Could we just use not LDA?
No, if you wanted the more substituted enolate, you got problems for the cross aldol, because then your base is only going to you would make the enolate under reversible conditions. You'd only make a small portion of it. By the time you introduce your second carbonyl compound, the base is still there. You're going to make the other enolate, and then you're going to have the mess. Yep. So it's sort of limited, right? You're using LDA, and so you're going to get the less substituted enolate. In this case, it doesn't matter because we've chosen our starting material appropriately. All right, second step is to incorporate your aldehyde, or your molecule that you want to be the electrophile. let's just for our purposes say it's this one. And here, the potential challenge that and the reason we're going to keep it cold is that the aldehyde alpha proton could be removed. In fact, the aldehyde alpha proton has a pKa of 17. The enolate that we just made in purple here is a strong enough base to remove the alpha proton from the orange aldehyde. You can tell because the pKa of the enolate's conjugate acid is 20. So we're concerned about something that I will call enolate exchange, where the alpha carbon of the purple enolate, instead of attacking the carbonyl carbon of the aldehyde, removes the aldehyde's alpha proton. So that's one of the reasons why we're running this at low temperature. We're going to keep it cold to avoid this enolate exchange. You don't want to make the other orange enolate. As soon as you do, you got all the same problems that we had before with the crossed aldol reaction and getting mixed crossed and self-aldol products. So, assuming we keep it cold, and in general that's, we're going to imagine that it works. The enolate attacks the carbonyl carbon. You get the new bond between the alpha carbon of what was the enolate and the carbonyl carbon of what was the aldehyde. And then you've got a negatively charged oxygen. Hydrogen of the aldehyde, and then the benzene ring. And of course, this can then pick up a proton in the aqueous workup step. And that will, I'm just gonna, since you've seen that mechanism before, I'm just gonna skip ahead to the aldol product, where that oxygen gets protonated. And then, of course, we could also draw the dehydration product. This is what happens when we do that E1CB mechanism to remove this proton, make the second enolate, and then electrons on that carbon kick down and kick off the OH group. And that would give you this dehydrated product, and you could also expect to see the cis isomer as well. We're not going to bother predicting in what ratio those form. Both the beta hydroxy carbonyl compound and the alpha beta unsaturated carbonyl compound are aldol products. You can draw either of them, and the answer is correct. In a synthesis, you are free to use either of them in a subsequent step. In a mechanism question, you'll know where you need to get to because the starting material in the product will be shown. All right, so that's the directed aldol, and again, if you're careful, it works pretty well. Yeah?
Seeing as we're in a polar aqueous solvent, how does the aqueous workup happen? Do we take it out and then put it into like water? Or
Yeah, so usually at the end of a reaction, when it's done, you can just add water. Sometimes it's water with a little bit of acid in it. Sometimes it's water with sodium bicarbonate in it. But yeah, you can add that directly to the reaction flask. You do it slowly if you got a strong base. But yeah, you add it directly. Then ideally your product is soluble in organic solvent, but not in water. Ideally the water and the organic phase remain separate. And you'll learn about this in 353. You can do an extraction to get your material. Yeah. Okay, others? All right. I told you last time, and a big theme of last time on Monday was that when we're using OH minus as our base in the aldol reaction, the aldol products are in equilibrium with the starting materials. So that means that the aldol products can, under different circumstances, go backwards to the enolate and ketone or aldehyde starting materials. So I want you to be aware of the retroaldol mechanism. I want you to know how to draw the mechanism for a retroaldol reaction as well. And in a retroaldol reaction, we're actually going to start with the alpha-beta unsaturated carbonyl compound, and we're going to end with the ketone starting material and perhaps OH minus. So the question is, how do we go backwards? And I'm going to be just last time we started here and we went here. So we're going to start here and go back. So starting from this alpha-beta unsaturated carbonyl compound and OH minus. If you remember from last time, the immediate precursor to the alpha-beta unsaturated carbonyl compound was this enolate. We called it the second enolate. And to get from this second enolate to the alpha-beta unsaturated carbonyl compound, we had lone pair electrons on this alpha carbon kick down and kick off the OH group. And that would get us here. So the question is, how do we instead start with the alpha-beta unsaturated carbonyl compound and then get to this second enolate? Where does my arrow need to start and where does it need to go? Just annotating this so you can see that it's an alpha-beta unsaturated carbonyl compound. If I want to go from here to here, what's my nucleophile? It's hydroxide, OH minus. That means the arrow's got to start with lone pairs on the oxygen. Okay, now what? It's got to attack the beta carbon. You can tell that because there's a bond here with the beta carbon that isn't in the starting material. Now let's rationalize that. Why does that make sense? When have you seen a nucleophile attack the beta carbon of an alpha-beta unsaturated carbonyl compound? Yeah, cuprates. In chapter 13, we had cuprates attack the beta carbon of alpha-beta unsaturated carbonyl compounds. And when they did, when the nucleophile attacked that beta carbon, we had to break the pi bond between alpha and beta carbons and move it onto the alpha carbon as a negative charge, where it would be stabilized by resonance in this enolate. Okay? So this step we would say looks like a conjugate addition step, or we've called that before a 1,4 addition step. We're attacking the beta carbon, and that gets us to the second enolate. The immediate precursor to that second enolate was the other aldol product, which is simply the beta hydroxy carbonyl compound. How do we get from the second enolate to the beta hydroxy carbonyl compound? Just got to protonate the alpha carbon, right? Remembering that the aldol reaction occurs under basic conditions, probably the only source of the proton is water. So yeah, we protonate on the alpha carbon. If you remember, the immediate precursor to the beta hydroxy carbonyl compound was the tetrahedral intermediate with a negative charge on what used to be the carbonyl carbon, on the negative charge on that oxygen. How do we get from the beta hydroxy carbonyl compound to its conjugate base? Yeah, that's easy, right? Deprotonation. We'll just use OH minus to remove a proton from that oxygen. All right, this conjugate base has a bond between alpha and beta carbons, and the immediate precursor to this one in the aldol reaction is the enolate and then a carbonyl electrophile. This is your nucleophile and this is your electrophile. How do I get from this intermediate to these two? What's got to happen?
Molecular
Kickoff, right? Electrons on the negatively charged oxygen kick down, and the leaving group's got to be the enolate. And the reason it can leave is because it's resonance stabilized. If I were to focus in on one important step for the retroaldol reaction, it would be this one. This is where we break the molecule apart into two pieces. So I will call this the key step. That's the Mountain America key step of the mechanism. All right. So then, lastly, to get from the enolate to the starting material, that one's easy. We just need to pick up a proton from water. And there we go. Okay, that's the retroaldol mechanism. Yes?
I think the second to the third thing that you drew on the left, you put like methyls and then you went to hydrogens.
Oh, thank you. Yikes.
Wow.
All right. Sorry about that. Actually, what I should have done is erase them, then say, no, I didn't, and be gaslighting you. That'd be good. All right, what else? Sorry, I'm going to keep that proton there. It's implied but not shown. Anyway, what else? Yeah?
In the end product you wrote like there's the enol plus the ketone.
Yeah. Sorry, in the end product I showed this ketone and then OH minus.
Oh, it's an end. Oh, I thought that said enol.
No, end, sorry. Poor penmanship. Good, what else? All right, the reason we're doing the retroaldol mechanism is because you will see in biochemistry, and then later on in chapters 27 when we do metabolism, you're going to see this as a key step in glycolysis. So I just want to, I wanted to move that up because I wasn't aesthetically pleasing. Oh well. So let me show you an example of a retroaldol mechanism from glycolysis. What I'm going to draw for you is fructose 1,6-bisphosphate. You don't need to memorize the structure or the name yet. That's coming in chapter 27. It's a 6-carbon sugar. You've got a phosphate group on carbon 6. You've got OH groups on carbons 5, 4, and 3. On carbon 2, you have a ketone, and then on carbon 1, you have a phosphate group. But the key observation here, if we start with the carbonyl carbon, this is the alpha carbon, and this is the beta carbon, is that fructose 1,6-phosphate is a beta hydroxy carbonyl compound. And therefore, it is, by definition, an aldol product. And if it is an aldol product, that means that it could go backwards to starting materials via a retroaldol reaction. So fructose 1,6-bisphosphate undergoes a retroaldol reaction. If you look up to what we had done before, the retroaldol reaction from the beta-hydroxycarbonyl compound simply consists of deprotonating the beta-hydroxy group to get to the negatively charged tetrahedral intermediate, and then you have the key kickoff step. And so what will happen in the retroaldol reaction is a base will remove the proton, and I'm not going to draw that in a separate step. I'll just erase and show the beta hydroxy group in its conjugate base form. Then electrons will kick down to form a pi bond, and the bond between alpha and beta carbons will break, and those electrons will move out onto the alpha carbon. And what I want you to do is draw, and I'll put this in the notes after the fact, draw what the two products of that, just that key kickoff step are. That reaction is important. You will see that it breaks the fructose 1,6-bisphosphate molecule with 6 carbons up into 2 similarly sized pieces, each with 3 carbons. And that's important for the subsequent steps of glycolysis. Interestingly, the enzyme that catalyzes this reaction is called aldolase. It's named for the aldol, not the retroaldol. And that's actually a common feature of enzymes in biochemistry. Enzymes don't care which way the reaction goes. That's determined by the equilibrium constant and by the conditions inside the cell. The enzyme just makes the reaction faster, and that's true for the forward and the reverse reactions. So you will sometimes see, and this is an example of an enzyme that's named for the backwards version of the reaction it's catalyzing. That's why it's not called retroaldolase. It might have been, but they just call it aldolase. And you'll see that all the time in biochemistry. Okay, questions about that? Yeah.
So is it possible for retrosynthesis to go from either the beta hydroxyaldol or the alpha beta unsaturated and then work your way to that?
That's right. In a retroaldol reaction, you may start either from this aldol product, the alpha beta unsaturated carbonyl compound, or the beta hydroxycarbonyl compound. Yeah. Go ahead.
How is this reaction favorable? If the normal reaction, it has to be at low temperatures and it has to be like with all these conditions in body temperatures, how do you make this reaction?
Okay.
In a body,
The
inside the body, how do you make this reaction?
Yeah, it's a good question. The reason we did in the directed aldol, we kept it at low temperature was to avoid enolate exchange, because we needed to control who was the nucleophile and who was the electrophile. You've rightly noted that the two pieces of this reaction are different. So in effect, the aldol direction of the reaction, going from whatever's over here to here, is a crossed aldol. Why can this happen at room temperature? Well, we only used low temperature to slow the reaction down and prevent enolate exchange. The enzyme is actually going to avoid all of those problems because its active site is going to position one of the partners close to a base where it can be deprotonated, and then the other partner in a position where it's going to be near the enolate. So by controlling the enzyme, one of the major things enzymes do is they control the location and relative orientation of the two reactive partners, and that prevents a lot of the undesired reactions. As to whether the reaction's favorable or not, at room temperature, the equilibrium constant happens to be pretty close to 1, so it can go forward or backwards. That's actually an advantage, but you'll learn about that more in biochem. Okay, others? Yeah. Okay. Good. So what we're going to do now is introduce a new reaction, but it's going to be very similar to the aldol reaction. The new reaction is called the Claisen reaction. It's like the aldol, but instead of using ketones and aldehydes, we're going to be using esters. And the key feature of the ester is that it's going to have a leaving group attached to the carbonyl carbon. So here's an example of the Claisen reaction. We'll use ethoxide, which is a relatively cheap base. It's matched to the identity of the group on the ester for reasons we've talked about before. That prevents, if we used OH minus, we would be concerned about the competing saponification reaction where OH would attack the carbonyl carbon. At least in this case, if ETO minus attacks the carbonyl carbon, we can't tell because either way, an ethoxide is getting kicked off. What will happen in the presence of this base is we deprotonate the alpha carbon of the ester. The pKa of that alpha proton is 25, meaning we form less than 0.1% of the ester enolate. And most of our stuff is still the ester starting material. And in the next step, that enolate will react with the remaining ester starting material like this, attacking the carbonyl carbon to get a tetrahedral intermediate. At this point, I'll start using shading so we can follow the different parts of the different reactants through in the product. In red is the new bond that we'll make. In purple is what used to be the enolate. Here's the negatively charged oxygen that used to be the carbonyl oxygen. Here's the OET group, and here's the methyl group. And in orange is what used to be part of the ester electrophile. Now, so far, that ought to look decently similar to the tetrahedral intermediate after an aldol reaction. The only difference is, unlike the aldol reaction where the negatively charged oxygen, or what used to be the carbonyl carbon, is not attached to a good leaving group, here there is one, or at least one relative to a negatively charged oxygen. So, that oxygen will act as a kicker offer to kick off the leaving group. And what we'll have effectively done in this step is, instead of addition, nucleophilic acyl substitution. That is, the enolate, the purple enolate, will have completely replaced the ethoxide group on the ester electrophile. This product has a particular structural pattern that you should learn to recognize. It is a beta keto ester. And beta keto esters are products of the Claisen reaction. In fact, this is one you've seen before. This one's actually called acetoacetic ester. And we use that in alkylation chemistry in chapter 17. And now your text is going to expect you to go back and do something similar. There's probably problems in chapter 18 now that require you to make acetoacetic ester and then do the alkylation chemistry from chapter 17. Now, as I mentioned, this first step, removing the alpha proton, is mostly favoring starting materials. And the attack step is reversible, and even the kicking off step is reversible too. That OET minus can come back in and attack what's now the beta carbon to generate this intermediate. What helps this reaction go forwards is actually something that you're going to look at and think is pointless, but it's actually it's realistically what happens. Notice that the proton, the alpha proton in the beta keto ester, is alpha to 2 carbonyls. And if you look up the pKa for the alpha proton of a beta keto ester, it is around 13. Your leaving group from the previous step is ethoxide. That is a strong enough base to completely remove the proton from the alpha carbon. Okay? And if you need convincing, let's just draw the conjugate acid of ETO minus, which is ethanol, which has a pKa of 16. And you can see you expect the equilibrium constant for this reaction to favor the formation of ethanol and this enolate by a factor of about 1,000. Now, fortunately, at this point, by the time we get here, all of the starting material has been consumed, so there's nothing else for this enolate to do. And if we want to isolate the desired beta keto ester product, all we have to do is gently adjust the pH to be lower than 13, and we will go back to the desired beta keto ester product. It'll pick up a proton from the water or hydronium that we add. So some of you are going to look at that and say, why on earth are we deprotonating only to protonate again? And the answer is you don't have to in a mechanism. You can stop here. But this is what actually happens in solution. And it's important because this enolate is very stable meaning that this is what sometimes people call a thermodynamic sink into which the reaction falls. Oh, there's a stray character in there. Thermodynamic sink into which the reaction falls. And once you get here, you're not going backwards. So this is one of the reasons why the reaction is pretty efficient. Okay, questions about the Claisen reaction? Yes?
Would you adjust the pH?
Sorry, say that one more time.
Is the pH greater than 13 or less than 13?
You want to adjust the pH lower than 13 so that if pH is lower than pKa, the proton is still on. All this would mean is you add water with a little bit of acid in it, and then you'll reprotonate that carbon. Other questions? Okay, well, the cross-Claisen has the same problems as the cross-aldol reaction. And so we're going to deal with the same sorts of workarounds as we saw before for the cross-aldol. And remember, by cross-Claisen, what I mean is I want to use two different esters, and I want one of them to be the enolate nucleophile, and I want the other one to be the electrophile. And not all of these strategies are equally useful, and we won't talk about them in a huge amount of detail. One of the options of dealing with the cross-Claisen is, of course, to use as an electrophile an ester that lacks alpha protons. We used this strategy, identical strategy before with the cross-aldol reaction. So as an example, suppose you want to use this, you want to make this enolate from this ester. That's fine. You would use ethoxide as the base, and you would know that you were only ever going to make less than 0.1% of that enolate. At this stage, you would bring in a second ester, and this ester, as you can see, lacks alpha protons. So you can't make the enolate from the orange ester. It can only be an electrophile. So, and we won't draw the whole mechanism, but you can hope that the enolate attacks, the purple enolate attacks the orange carbonyl carbon, and you can hope in the end to get this Claisen product, which I'll abbreviate here. And that Claisen product comes from attack of the purple nucleophile on the orange electrophile, and in red is the bond that you make. Now, you should still be worried about the self-Claisen product of that purple ester, purple enolate, which would just be this beta-keto ester. But at least you've got a shot at getting the right thing. Not a perfect workaround, but you can use it. A second approach that that you can use for esters, and this is sort of new, we didn't necessarily do this for the cross-aldol reaction, is to use as an electrophile an especially electron-poor ester. So here's an example of an especially electron-poor ester. This is a molecule you maybe haven't seen before. It is called diethyl carbonate. Notice how the carbonyl carbon in the middle is attached to two OET groups instead of just one. This is like a diester on the same molecule. And that carbonyl carbon is somewhat electron poor, more electron poor than an ester because of the two electronegative oxygens. So it also lacks alpha protons. So when you bring in the purple ester nucleophile, you can hope that it will attack, rather than attack the ester starting material, because this is more electrophilic than that ester starting material. You can hope that the negatively charged enolate will attack the carbonyl carbon to give you a tetrahedral intermediate. And now, when you get to that tetrahedral intermediate, one of the things you see is that what used to be the orange carbonyl carbon is attached to two leaving groups, and they're identical, so either one can leave. We'll show that one. And when you're done, you're left with a beta carbonyl ester, but actually the thing you just added has an ester on it as well. You've seen that molecule before. That's called the malonic ester. We use that as starting material for some alkylation chemistry in chapter 16. This is one way to make it. And again, your text is probably going to have you practice synthesis by starting with this ester and diethyl carbonate, making the malonic ester, and then doing that alkylation stuff and decarboxylation stuff that you learned in chapter 17. Yeah.
What's to stop another enolate from coming in and kicking off that other?
So yeah, what's to stop another enolate from coming in and attacking this one and doing another Claisen reaction? The answer is really, that was a possibility up here too. The answer is really what I told you. As soon as this forms, this base gets consumed by the alpha proton, so there's no more enolate at that point. Yep. Go ahead.
Another question about how that molecule is more electron poor.
Yeah.
Does it have more resonance stabilization?
Yeah, it's got more resonance donation due to those lone pairs, so it's kind of a trade-off, and I'm not sure how to reason through which one matters more. I agree it's perplexing. Some carbonates are stable too, so it's some of your plastic bottles are actually carbonate-based polymers, and those aren't falling apart all the time. So it's tough to say. This one works. I'm not sure why others don't. It's a good question. Yeah.
Would we ever use LDA?
Would you use LDA? You could. You don't need to, because it works fine with just the cheaper base. Another example of an especially electron poor, this one will make a little bit more sense than the diethyl carbonate, an especially electron poor ester is this one. It's going to look like a close cousin of diethyl carbonate. It's actually called ethyl chloroformate. This is like a hybrid. It's an ester on one side and an acid chloride on the other. So you can sort of tell where we're going with this. We could use the same enolate starting material, have it attack the carbonyl carbon to give a tetrahedral intermediate. And in that tetrahedral intermediate, you'll see that there are two leaving groups on what used to be the carbonyl carbon. And what's going to happen here is the best leaving group will leave, and chloro is a better leaving group than ethoxide. And so that's a strategy that can actually get you to the same malonic ester product. Again, not that versatile. It only is good for making the malonic ester, but it's one of the things you can do if you want to do a cross-Claisen reaction. All right. So with that, I want to talk about an intramolecular version of the Claisen reaction. We did this for the aldol reaction as well. But this is going to be simpler because esters only have one alpha carbon. In the intramolecular aldol reaction, if we were dealing with ketones, we were worried about which alpha proton gets removed. Not so with the esters. There's only one alpha proton that can be removed for an ester. So let me show you what I mean by this. I'm going to draw a 6-carbon diester. So we're going to have an ester on this side, 1, 2, 3, 4, 5, 6, and then an ester on this side. Now you'll notice that both of those esters are identical by symmetry. I could do steering wheel action to turn the molecule around 180 degrees and I got the same thing, right? Ester on carbon 1 is identical to the ester on carbon 6. That means this alpha carbon is identical to this one. So I'm not going to worry about which of those two alpha carbons gets deprotonated because they're identical to each other. Notice I also don't need to worry for this ester which side it gets deprotonated on because there's only one side with alpha protons. So in the Claisen reaction, we will remove one of those alpha protons with ethoxide. That's going to make our enolate. We'll redraw the molecule here. Now we're going to pay attention to the alpha carbon, and we're going to count from the alpha carbon 1, 2, 3, 4, 5. The alpha carbon of the enolate is going to attack the other carbonyl carbon, just as we would in a Claisen reaction to give a tetrahedral intermediate. That's going to make a new bond between the alpha carbon and carbonyl carbon 5. And because of that, that's going to make a 5-membered ring. So we can draw the product of that reaction just drawing a pentagon, 5-membered ring. We'll choose one of the atoms to be carbon 5, 4, 3, 2, and 1. 1 is also the alpha carbon. Carbon 5 should have the negatively charged oxygen of the tetrahedral intermediate, and it should also have this OET group. Then carbon 1 should have the ester. Then electrons on the negatively charged oxygen will kick down, kick off the leaving group, and you'll be left with this beta keto ester. It's a Claisen product, and you may want to work through this or try examples of this with different lengths of between the esters. I know that sometimes when you make a ring, that's difficult for you to do, and so you should practice it until it isn't. This beta keto ester was actually the starting material for the worst reaction I ever did in grad school. It turns out I needed to take this starting material and make an imine with the ketone in a subsequent step. I was trying to make an amino acid. A colleague of mine who graduated shortly before this time had done a reaction similar to this on a huge scale, and it had really enabled his grad studies because he didn't have to keep going back and doing this reaction again and again, taking days at a time to prepare starting materials for subsequent things. So I thought, like Obi-Wan said to Luke, I thought I could train Anakin as well as Master Yoda, and I was wrong. I thought I could do a large-scale reaction just as well as my friend Justin, and I was wrong. So I set up the reaction in a huge 20-liter flask, dumped in the beta keto ester and the amine to make the imine, and walked away, and it eventually sort of bubbled over and oozed stuff down into the fume hood and down the sides of the cabinet outside the fume hood and all over the floor. I had to spend the better part of a night cleaning all of that up, and then I had to stand before the research group and my advisor and confess my sins and explain what I had done wrong. I had to be the less effective example. You ever seen that demotivator? It could be that your purpose in life is to be a cautionary tale for others. That's how I felt that day. So, yeah, it turns out, I mean, that I would make that kind of mistake is not surprising. I'm somewhat clumsy, so it tracks that that would happen. And I've sort of learned from that experience. What my wife says doesn't track is that she knows I'm a klutz. She knows I trip. She knows I'm sort of absent-minded and forget things. What she can't understand is I'm a organist, not a good one, but I play the organ in sacrament meeting, and I use the pedals, and she's like, it really doesn't track that you can pull that off with the hands and the feet at the same time. I'm like, I know it doesn't. I'm not sure how it works. So anyway, well, with that, I want to show you an example of a Claisen reaction from biochemistry. We'll deal with this in later in the chapter on metabolism. This example comes from a molecule that you saw in your exam. It's a thioester in which the thiol is connected to something called the acyl carrier protein. And we'll abbreviate that as ACP, but this is just a large thing that you can think of as an R group. And nature will take an enolate, where also from a thioester. We won't worry about what that particular R group is. And that enolate, nor will we worry about where the enolate comes from. There's more to the story, but that's all we'll say today. Attacks the carbonyl carbon. You end up with a tetrahedral intermediate that looks like this. Here's the purple enolate that we started with. And then here's the new bond we just made. Here's the negatively charged oxygen, methyl group, and sulfur attached to the acyl carrier protein. Electrons kick down, kick off that leaving group, and then you end up with a beta keto thioester. And nature will do subsequent steps that we'll learn about later that actually reduce the ketone all the way down to the alkane. And then this, it's almost as though after these reactions, and this is the step that's the Claisen step, it's almost as though after these reactions you have taken your starting thioester and elongated it by 2 carbons. And this is actually how fatty acid synthesis happens in biology, because you can take this thioester and use it as the electrophile up here for another enolate to attack. And you can tack on another 2 carbons and go through the cycle again multiple times. One thing to point out about thioesters, as we learned earlier, they're more reactive than esters because the thiol leaving group here, its conjugate acid has a lower pKa than that for alcohols. All right, so that's nature's Claisen reaction. What we want to do next is introduce the last new reaction of chapter 18, which is called the Michael reaction. This is an example of, another example of a conjugate addition or attack. We will see that the Michael reaction is attack of an enolate on the beta carbon of an alpha beta unsaturated carbonyl compound. So we're bringing together multiple threads at this stage. Here is an alpha beta unsaturated carbonyl compound. Carbonyl carbon, alpha carbon, beta carbon. And where we're going next is using an enolate, and I'll just choose this one, in which the alpha carbon of the enolate is going to act as a nucleophile and attack the beta carbon of this alpha beta unsaturated carbonyl compound. Before, when we've had nucleophiles attack beta carbons, we've broken the bond, we've made a new bond with the beta carbon, and then we put the electrons from that alpha beta bond on the alpha carbon. Here, the nucleophile is simply going to be the enolate. So we'll draw an arrow from the alpha carbon of the enolate to the beta carbon of my electrophile. And the product will look, or the intermediate will look like this. Here is the new bond we just formed. Here is the beta carbon. Here's the alpha carbon that now has a negative charge on it, and here's the rest of our molecule. Then we'll pick up a proton from water on that alpha carbon to give us the product. And we'll have more to say about that product's identity, how to recognize it, and a little bit more about the Michael reaction next time. All right, see you Friday.